Okay, in this lecture, we're going to learn a pretty cool method in order to solve for the potential and then eventually the electric field in a region of space. It's called the method of images, and it kind of uses a trick that's a little bit related to optics and the idea of a virtual image right behind a mirror. Basically, what you're going to do is you're going to use fake image charges. So not real charges, but you're going to be like, what if I put a fake charge here in this region of space? If that charge configuration satisfies the boundary conditions of this space in which you're trying to solve the potential in, the uniqueness theorem, which we just talked about, basically says that is the solution to Laplace's equation. That's the solution to this equation where you can find the potential, and then, right, if you wanted to, you could take the gradient, negative gradient of the potential to find the electric field. Okay, so there's really only a few special circumstances where this can be used, at least in an easy way. If you're really creative in imagining these charge distributions, you might be better at this. But in this class, we'll talk about a few special, simpler circumstances, but it's still a useful technique. Okay, so the basis of this particular technique is to use the uniqueness theorem, which I didn't really derive in the lecture because it's derived pretty well in the book, and that's mostly just kind of a math derivation, in my opinion, or a math proof. I think it's satisfactory to just believe it. Okay, we're going to use this uniqueness theorem, which says that if I find a potential that satisfies the boundary condition, it is the solution. It's the only solution. Okay, so we're going to use that, and you get to use your imaginations. There really isn't a better way to do this than just to think about it and figure out where to put these fake charges to solve a limited number of problems. Okay. And most of the problems will, like a lot of the simpler problems in this class, they're going to involve conducting maybe planes or sheets. It could be a sphere, okay, or cylinders are simple enough that you could use this technique, okay. Okay, so the idea is if we find a V that satisfies, in general, I said Laplace's a lot, but in general, Laplace is just a special situation of Poisson's equation. So if it satisfies this guy, which is Poisson's equation, and the boundary conditions, which I'll just write as VC, then we have the one and only correct answer, okay? All right, so let's imagine a scenario where we'd actually use this. Okay, so I'm going to draw just a conductor that's got a flat surface here, and make it like a beam looking thing, okay? But I'm drawing it pretty limited. Let's pretend like this thing goes out more or less to infinity, or at least it's really, really big, okay? This is a conductor that is grounded, which means it's hooked up to some reservoir of charge in order to keep the potential at zero, okay? And just to make it clear, this is a conductor, which means that the electrons are free to move about, okay? Okay, so this is my setup. I'm not quite done yet though, because I'm going to put a charge, a positive charge, at a position D, okay, from the face of my conductor here. Okay, so let me draw that. Let's do it like this. This distance is going to be a distance D. Okay, so I've got a charge at distance d from the face of a conductor. Okay, the question is, what surface charge will we induce on the conductor? Okay, as I'm recording this, we just did a Zoom session where we talked about conductors. You guys did your tutorial. And right, we thought in general how charge would reconfigure in a conductor. I think you guys could tell me that if I brought this positive charge here near this face of a conductor, you'd get some negative charge. But you probably couldn't tell me exactly what the charge would be. Okay, so for example, you probably couldn't answer, for a particular region, what our surface charge density would be. So how can we solve this problem? Well, we're going to use what's called the method of images to figure out what that surface charge would be. Okay, first thing I'm going to do is I'm just going to define a coordinate system here. Just to make this a little bit more clear, z is going to be along the plane in the up direction. Y is also along the plane. And I'm going to have x, it's a little bit off. X is going to be pointing perpendicular to the plane, okay? So the charge, this distance here, is going to be along the x direction, okay? And I have some boundary conditions that I can define, okay? So let's define those boundary conditions. Okay, I know that the potential is equal to 0 in the conductor and on the face of the conductor. Okay, that's given by the fact that this conductor is grounded. Okay, I also know that the potential at infinity, and actually let me write this. If I put my origin right at the conductor, then I can say that's also the potential at x equals 0. If I let x go out to infinity, I'm going to assume that the potential is 0 at infinity, which makes sense because I'd be really, really, really far away from this positive charge if that was the only one. Okay, and I also know that this system, it should satisfy Poisson's equation. Okay, and Poisson's equation, right, let's write it out one more time, says that. Okay, so the Laplacian, which is this guy, of the potential is equal to the negative of the volume charge density over our permittivity of free space, epsilon naught. Lots of words, okay? All right, but I'm going to solve this. I'm going to solve in what I'm going to call the right half, or for x is greater than 0 only, okay? All right, and that's important because when I'm using this image method, I can only really solve for the region of space where I'm not going to put a bunch of these fake charges. And you guys will see I'm going to put fake charges in the space where x is negative. So this is only going to be true where there's real charges, no fake charges. So I can only solve it in the right half of my picture here. But that's the only place that I really care about where the potential is anyways. Okay, so now I have to be a little bit clever about this. I'm actually going to move this up here. Okay. And I'm going to think a little bit about my boundary conditions. I know that the potential is 0 where x equals 0. Okay, so all along this plane here. I know that the potential is at 0 at infinity. Okay, and I know that it satisfies Poisson's equation. So I can come up with another solution using this fake charge that actually satisfies those same conditions. And again, there's no better way to do this than just thinking, right? Using your imagination. So I want you to imagine that now, and I'm going to draw this from the side, this is our z-axis, and this is our x-axis here. Okay, I still have our positive charge out here at a distance of d from the origin. Okay, if I wanted to come up and put another fake charge here that would satisfy these boundary conditions, then I need to put the charge, my fake charge, I'll make it orange, on the other side. Okay, just like a virtual image on the other side of a mirror. Okay, of my x-axis. And in both cases, they're going to be at a distance of d. Okay, so this is also at a distance of d. Okay, actually I'm going to do that a little bit differently because that is going to get confusing later. Let me write this as this is at a position of negative d, 0, and this up here is at a position of d, 0. Okay, so I know because of the way potential superimposes that this potential is going to be is going to cancel out because this is going to produce a negative potential and this is going to produce a positive potential. It's going to cancel out all along this line between them. Okay, everywhere where the r from these two, right, if I pick a point up here, the distance between these two is going to be the same, right? So when I calculate the potential, which would be given by this equation here, okay, one of these potentials would be opposite negative, one would be positive, but they would have the same value, so they would superimpose and cancel out all along that line. Okay, that should make sense. Okay, and if I go again all the way out to infinity here, it still makes sense that my potential is 0 at infinity. So I've satisfied these boundary conditions. So for this space only, for only this space, okay, the solution satisfies our conditions. Okay, I can't really say anything about this space here. This is just doing the business, but it's basically, it's going to kind of reproduce a similar, right, effect on this right-hand side that the redistribution of charge would do on the plate itself. But I can't actually solve for the potential over here because this is fake news, okay? Not really happening. Okay, so let's say I just wanted to know the potential at some general point P up here, which I'll just say is at X and Y. Okay, if I want to solve for the potential at that point, I need to find some position vectors from each of my charges here. So I'm going to do that. Okay. And now if I want to find, let's see, let's write this. Potential at X and Y, which I'm just going to call V sub R here, it's going to be equal to Q over 4 pi epsilon naught, okay, times, I just pulled out that common factor, times our 1 over, right, the magnitude of our one separation vector, okay, plus 1 over the magnitude of the separation vector from our positive charge. Okay, and I can write that out, what those are. Okay, if I look at my picture here and I remember that the charges are each a distance of d along the x-axis away from the origin, then I can write that position vector as, for the negative charge, oops, sorry, one of these needs to be negative. This one's negative. Boop. For the negative charge, the position vector is going to churn into x minus d. Okay, remember what I'm doing there for that. If you can remember, let me do it over here. This is our separation vector. It's equal to r minus r prime. In this case, for this one, r is going to be equal to x and y. That is just this vector from the origin to the point where we're trying to solve the problem. Our r prime, that's the vector that goes from the origin to our point charge. So that is going to be equal to negative d y, or sorry, 0. Excuse me. Okay, so when I subtract these two, this one from this one, okay, hopefully that makes sense what I'm getting for my separation vector over here, okay. And I didn't do that in 3 dimensions, but the z also does the same thing as the y, okay. So I get the square root on the bottom here of x minus d plus y squared plus z squared. That's for my negative one. Run out of room. Okay, and my positive real charge is going to give me a separation vector of x plus d squared plus y squared plus z squared. Okay, so this right here is what I get for the potential anywhere in space. I can pick anywhere in space up here, and I've just solved for the potential, okay? So it's kind of amazing. This was not that hard of a problem to solve if you guys remember how to do separation vectors, okay, and add those together. So again, if you don't remember how to do that, take a moment, write it out in your notes, make sure you understand it. But as long as I'm in the positive x space here, this is the right potential because I've found a potential that satisfies my boundary conditions, satisfies Poisson's equation, okay, which I haven't really shown, but it has to because I'm just superimposing charges here. Okay, therefore it is the unique and only solution to the problem on the right-hand side. Okay, so what is our method in general? So the method in general for your method of images, so this is our, let me write this out, this is the method of images method, okay? Method of images method is to find a new, but not real, just a new configuration by adding image charges, which are fake charges in strategic spots so that the resulting potential satisfies the boundary conditions that you have, that you know you have for your real problem, okay? The caveat to this is you can't solve, so you can't solve for the potential in the region you put the fake charge. Okay, so for example, I put the image charge in the region where x was less than 0. I couldn't have solved for the potential and gotten the right answer there, right? Because obviously in the real problem, there's a big conductor there. And so, right, it's an equal potential in here, and it wouldn't look anything like if you had just a negative charge in space, okay? So that's the first step. You just have to do that, but then you have to realize you don't want to put any of those charges in the region where you're actually interested in calculating the field. That's going to go against the method because you won't actually be able to say what the potential is in that region, okay? The next step is just write out, right? If you're just using point charges, then you can just use this equation here to calculate the superposition of the final potential of those individual point charges. So depending on how many you needed, you could need more than one. I just had one in that example, but in lots of cases, you might need more than one in more than one different place. Of course, all of them put in a region where you're not actually trying to figure out what the potential is. Okay, and then just sum them together, okay? So some of these charges will be real, and some will be fake or images. Okay? And that's okay. And again, I'm just going to say this one more time because I have it in my notes. Only valid in limited region. Okay? And it can't contain any of those fake charges. All right. So that's like not that bad. That's what I can do to solve for the potential. Again, if there's more than one charge here, then you got to do more than one of these. Okay, could get complicated, right, with a lot of terms summed together. But in terms of setting it up, again, you just need to figure out the position vector, or sorry, the separation vector for each of the potentials, and that comes from remembering how to define those position vectors. Okay, so try to remember how to do that. That's, again, pretty fundamental to a lot of what we have done so far in the class. Let's have a little bit more fun with our solution. We haven't really solved anything that interesting. We found the potential in the space to the right of that conductor. Okay, let's do something more fun. Let's use that to find our surface charge density on the face of our conductor. So that positive charge, when we brought it near, it polarized the conductor. It's going to pull some electrons from inside the conductor out to the surface. We want to figure out what exactly that charge density looked like. Okay, so in order to do this, we're going to recall, hopefully, okay, that the electric field just on the outside of a conductor is going to be equal to, and now we're worried about the xz plane, so along this xz plane, so along, let me go back to the picture here, so along this plane here, that's the yz plane, that's where we want to solve the surface charge. So we know the electric field is going to be that surface charge divided by epsilon naught. In this case, it's going to be in the x hat direction. Since we've induced some negative charge, it's probably going to be in the negative x hat direction, but we'll just figure that out by actually solving for that being negative or positive. Okay, so this is true just outside the conductor. Cool. Okay, we also know that E is equal to the negative gradient of our potential. We've been using that one for a while. Okay, so we know that sigma over epsilon naught is equal to the negative gradient of our voltage in the x direction at x equals 0. Okay, so that tells me that I want to take the gradient of the potential with respect to x, and that's going to be equal to what the electric field is equal to, which is related to the surface charge density. Okay, so this is a way I can relate the surface charge density here to the rate of change of the potential just outside the top of this conductor. Okay, so let's go ahead and take that derivative. Okay, it's not that bad. But if you wanted to check your work, doesn't hurt to be good at Mathematica or something like that. Okay, we end up getting sigma over epsilon naught. Okay, go back here. I'm going to actually copy and paste this over so you can see what I'm taking the derivative of. Let's see here. This is what we're going to take the derivative of. And this is x, y, z. Okay, but I'm only going to take the derivative with respect to x and its partial derivative. Okay, so when I do that, first I'm going to get a negative sign. That comes from here. I'm going to pull out those constants again that are in every term. Okay, and then if I look at what's in the square brackets, I'm going to get a negative x minus d, okay, divided by all of the stuff on the bottom. Let's see, I need one more there. this is going to be now to the 3/2. And similar on this side, just a little different. Oh, wait, that's not what I want to do. Okay, now, if you can imagine what this is going to look like, this is going to be x plus d squared plus y squared plus z squared to the 3/2. Okay, I could have written that out with a little more room, but whatever. Okay, and this is true really just above the sheet, okay? Or sorry, this is true on the sheet itself. So at x equals 0, right at the sheet. So I can simplify this even more by setting x equal to 0 if I want to figure out what the potential is right at the sheet. Okay, so let's simplify this even more by plugging in x equal to 0. And when I do that, it simplifies quite a bit. I just get 2 up here. Down here I get d squared plus y squared plus z squared, all of that to the 3/2, okay? Let's see. Sorry, I can cancel that out. Let me make this even simpler still. And I get sigma. Again, this is on the sheet, so at different y's and z's is equal to negative q d over 4 pi times all this business. And if I was being really careful, I would make sure that the units work out. I think so, because I end up getting units of, if I look down here, I end up getting units of distance to the 3rd, and then over here I've got a distance up top, so I end up getting charge over distance squared. So that seems good. I think I did everything right. Okay, what does this surface charge density look like? Well, I can look at this equation for a bit. I could plot it in Mathematica, but I know that it peaks at the origin, or where x is equal to y, which is equal to z, which is equal to 0, which means, of course, it's peaking right here. And of course, it's negative, so the most negative surface charge density is right here, opposite to where the charge is, okay, and then it falls off from that point. But if I really wanted to know what it was for some application, right, I could go into a computer program now and plot, right, and it would be strongest there, and then it would fall off with some distribution, and it would be negative. I'll put some negative signs, okay? It'd be prettier to do that in Mathematica, but I'm kind of Mathematica out for this particular week.